Okay, hi everyone. Today we're going to solve another problem that is LeetCode 144 binary tree traversal, and it's in a pre-order fashion. It's a good problem, and I think in a lot of tree problems, traversals are very standard techniques that are used to solve them. So in that regard, it is kind of an important problem to understand some concepts, and it's a easy level problem, but still it has a very good like to dislike ratio. So let's start. So we are given a root of a binary tree. We need to return the pre-order traversal of its nodes values. For example, we have 1, 2, and 3. The pre-order traversal will be simple 1, 2, 3. And so let's understand first what is pre-order traversal. So let's say we have this tree that is 1. Now you have 2. Then you have 3. Now you have 4, 5, and let's say 6. So this is the tree that you have. Now the pre-order. So basically there are three traversal. One is pre-order, another is in order, and then you have post order. I'm not going into detail for these two because they are not required in the question. I will be talking about pre-order. So pre-order basically means that from root to children's, and that could be a right child or left child, right? So let's understand this. So we make this preference that when we are dealing with the right or left child, we will be taking the consideration of left child. Okay. So for example, now you are at this node. We have marked this node, and so we will have first of all 1 in our root vector, and then we will have, now because we are taking the childs now, and I'll be giving preference to the left child, right? Let's say child preference is left child, and then you will have right child. So left child of 1 is 2, and then you have a right child that is 3. And now we will recursively do it for 2 because left child was a preference, so we will recursively solve it for 2. And for 2, the root value, yeah, basically we will not be putting them into the nodes vector now. We will have, although we will have 1 as a value that is inserted, but the child value will not be inserted. So preference means that we will recursively call on these childs. So now we'll recursively call on 2, and then we will have 2 value. Fine. After 2, we will have 4 and 6. So it will be like a recursive function, and this is the recursive stack. First we have function 1, right? And from function 1 is not over yet, but after function 1 we have stored function for row no, 2, and we have stored for, so now we have f of 2, and we will be solving it for f of 2, and f of 2 will give us these childs, that is f of 4, right? And f of 4 will say that to, because now we are pointing on f of 4, f of 4 will say that this is the root value, please store it, and we will store it in our nodes. And from f of 4 we don't have any node child, right? Which means that we will now backtrack to 2, and at 2 we have stored the first preference that was a left child, but now we will be working on, because now f of 4 is over, we will be kicking it out of the recursive stack, and now we will be storing f of 5. And f of 5, it also, f of 5 does also, I mean the node 5 also doesn't have any children, so we will not be storing anything in the recursive stack, and we will have 5 as it is. Now we will backtrack to 2, and I will say that f of 5 is completed. I will say f of 2 is also completed. When f of 2 is completed, which means one child processing of 1, which means node 1 has a child that is a left child as a 2, and its processing is done. So let's move to the other child, that is right child. So now I will process this node, and I will recursively call it on f of 3, and f of 3 I don't have the left child, so I will not be calling a recursive call on left child, but I will be calling a recursive call on right child because I do have a right child. And by the way, I will also be storing the 3 here because we are concentrating on this node. And now we are at f of 6, so we are now focusing on f of 6. Recursive stack will have f of 6, f of 6 doesn't have any child, so it will be popped out, and we will be storing f of 6 because we are concentrating on it. And then we will backtrack to 3, and I will say that f of 3 is also completed, and then I will backtrack to 1, and I will say that both of the childs are processed, so it will be popped out. Now the recursive stack is empty, and these are the nodes that we want. And one way to verify it, although I will not consider it as a very good option, because this is like a not this doesn't have any proof basically, this method, but I do use it. I have not, and this method hasn't failed me anywhere. So if you are using a pre-order traversal and if you want to verify, then I have a very strong thing that take this finger and point it towards this and point it toward the right side, and keep on going through these nodes and verify. So for example, we have 1, fine, we have 2, fine, we have 4, fine. Now I will go back, and then we have 5, fine. I will go back, and then we have 3, very good, and now we have 6, and then we are out, which means that now we are out, basically now we are here, which means that this is a correct sequence. So let's code it up. First of all, we need vector of int nodes where we'll be storing the nodes, and then I need a pre-order function, and it will have a root as one argument, and the other arguments will be nodes. And then after filling up the nodes with the pre-order function, I will be returning this nodes vector. Now to construct this pre-order function, I will say void, because it is not returning anything, and the first argument is a tree node pointer root, and another argument is vector of int nodes. Now if root is equal to null, right, in that scenario we just need to return, because it's a void function, we won't be returning anything, and we don't want to process anything. And if it is not null, because it's a pre-order function, so we will be doing our business here, and then we will be calling pre-order function on the left child, because that is the preference, and nodes as it is, and then we will be calling pre-order for right child and nodes as it is. Now what we want to work, the logic is that in nodes we are going to push back the root value, right? We're going to push back this value, and hopefully our nodes vector will be constructed and it has all the values of the nodes in a pre-order fashion, because this traversal is in a pre-order fashion, and we will have our answer. So let's see if this will work. Okay, test cases are passed. Okay, it does work, and it's not performing very good. So let's see how we can optimize it. Although I will say that there is no optimization, but we can do it iteratively. In some compilers, in some programming languages, recursive functions, recursive calls are not very efficient. So because of that, we will be doing it iteratively. So how to do it iteratively? Let's see. Now I will say that if root is null, if root is null, then just return an empty array, because we don't have anything if there's root is null. And we also need a stack. So I will say vector of int, not int actually, we will need a stack to store the tree nodes, and this is st. So st will be initialized by pushing the root node into the stack. Now this is not something that we are going to use. So while st.empty is true, st.empty is false actually. Until and unless we have some elements into the stack, we have some nodes into the stack, then we are going to process it. And how we are going to process it? So first of all, we're going to extract the top node. So we will say current node is equal to st.back. If you are using an STL stack data structure, then you can use st.top, but I'm using a vector, so st.back. And then you will pop it out, pop back. Now when you have this current node, so that was our main cause, right? When we are concentrating on a node, then we are storing into the nodes vector. So I will say nodes dot pushback current node value, right? Now in in iterative version, the preferences, how we are pushing it into the stack, will be changed. Why it is changed? Because let's say that, because the top element, because okay, first of all, let me write the code and then I will tell you why the order of the lines are not as much as you were expecting it to be. So if you have a current node and you have a, let's say, right child, right, then you will be pushing back that right child, sorry, right child, not value. And the same thing is for the left child, right? Now why we are pushing right first and then left? Because we want to use the left child first, we want to process the left child first, because in iterative version we can process the left child first by having the recursive call made to the left child as in the first order, is in as in the priority order. But in this case, in the iterative version, so we are having stack, right? So let's say I am on this node. Now I will be taking this 3 first. So let's say I have 1, but now I have removed 1. And then I'll be taking 3 first, and then I will taking 2 first. Then I will take 2, right? Because in that case, I will now be processing left child first, and then after this left child is processed, it will be popped out, and now you will be processing the right child. So because of that, we are going to store the right child first and then left child. And then hopefully we are returning our nodes. I think this is good. So let's see if this will work. Okay, it does. And okay, it is submitted, but it is not performing well. I don't know why, but yeah, I think these are the only two methods to solve this problem. Yeah, we can do it iteratively. We have done it. So this was the iterative code, and I hope that this was clear to you. If you want to get a particular solution, get a particular problem to be solved, then you can obviously comment it below, and you can also find the solution and the code in the description. So yeah, thanks for watching and have a good day.